I mean, we need to ensure that we really don't want switches to move. You shouldn't be able to throw a switch or change its position when a train is supposed to pass over it. I mean, suppose we have a train that comes here and it's supposed to go straight ahead, but now the switch is thrown into the current position, then that would be an invitation to trouble. So hence this requirement here that switches can only be moved when they are not in a locked route, because if you remember, the locking of the route, that's the first thing you do if you want a train to travel on the route. You lock it. So as long as this route is locked, for instance, then this switch is not allowed to move. And lastly, we also divide the routes, or the rail yard, however you want to see it. It's also divided into tracks. This TC1, TC2, TC3, TC4 in the picture. And for each of those tracks, there is some kind of device for detecting whether there's a train there or not. And in the old days, or even now, the traditional way, the traditional device for doing this is something called a track circuit, which is basically you hook up an electric current in the two metal bars and a relay. And when the train enters, it will form a closed circuit of electricity and the relay will pull. So then the signal system would know that you actually have a train on that track. So this is the general idea of how signaling systems are supposed to work. So you take this one train only idea, but you divide it. But instead of having the whole rail yard as a big area, you divide the rail yard into smaller bits to routes. And then for each such route, you only allow one train at a time. And that's how you avoid the collisions. There's, of course, more details here, but I'm not going to dwell on those more. I think you know enough to get the general idea. So that's the technical thing about signaling systems. And if we look at the sort of application of it, or these, not just the technicalities, but how it's supposed to be done when it comes to who's buying them, who's providing them, what's the surrounding context there, then not very surprisingly, signaling systems are surrounded by rules, regulations, and standards, since they are safety critical systems, and they do exist in order to protect and save lives. So there's you cannot install, if you want to have trains running around, that's not something you can do as you pleased. There are lots of things that you actually need to comply with. And those rules and regulations and standards, they concern both the actual functionality of the signaling systems, in these things with routes and stuff, for instance. That's usually mentioned as, that's kind of a part of these regulations. But they also concern the design process of signaling systems. What kind of steps and measures do you actually need to do when you are making, if you're a supplier of a signaling system? And usually then it's the infrastructure manager, the IM, that's the one who's in charge of these things. And when it comes to this design process, what the suppliers of signaling systems, what they actually need to do in order to comply, it is surprisingly a lot that they need to do. And in particular, it is surprisingly a lot of documentation that needs to be provided, since they have to, in principle, what they have to provide is an evidence that the system they deliver is actually in compliance with the requirements of the infrastructure manager. And since it's not a legal thing, or it is legal, but you do have to show that you have actually verified that whatever requirements the infrastructure manager has, your signaling system is complying with it. And that documentation then, in order for the infrastructure manager to actually accept whatever system has been delivered, they will also be approved by an independent safety assessor, meaning that there's a third party involved here as well, that is supposed to go through all this documentation and check it and see that it actually makes sense and that it actually does what it is supposed to do. Yes. So, which brings us to the point where verification. So verification plays a very important part when one is making, or when one is dealing with signaling systems. Okay, so just to say something really, to state the obvious. So in general, verification means that we establish or prove something. And in this context, what we do have is some kind of system with some form of requirements. And what we want to ensure is that this system actually satisfies these requirements. And of course, this is just a very general statement, but when it comes to signaling system, these usually have quite concrete meaning. And it is concrete, both the system, the signaling system in this case, is sort of, it's not an abstract thing. It's a concrete machine of some sort that does something. And those requirements are actually, they should be stated in such a way that you can actually verify that the signaling system fulfills them. Which means that you can start to contemplate or apply formal verification to do your verification. And in order to do formal verification, or at least in the sense that I'm talking about it, what I mean then is that one make the verification problem that we had, whether the system fulfills the requirement, we like to turn that into a mathematical problem, meaning that we model the system and we model the requirements, both in terms of mathematical logic, and then we use special software or dedicated software that can provide the answer whether the system fulfills those requirements, or rather the model of the system fulfills the model of the requirements. So then model checkers, they are, as I already said, that they are special kind of software which takes formulas R and S and tries to construct a proof of R from S. So in this case, so you assume something, in this case the system, and then you try to prove the requirements, the R formula thing. And this now comes an important restriction here, that these formulas are not arbitrary. They need to be formulated in propositional logic. It can be timed propositional logic, that's fine, but it cannot be a more powerful logic than that. And this will have implications, as we will see further on. So you feed your requirements formula and your system formula into the model checker, and then after a while, which can be quite long, it will provide you with an answer. Either you get a yes, meaning that there is a proof that the requirement is fulfilled by the system, or it will tell you no. And in the case of a no, you will also get a counterexample, which is a concrete, a structure where, or an assignment of values to the variables involved there, and for the given time steps, which leads you to a situation or a state of the system where the requirements are not satisfied. So let's say something about modeling of the system. When it comes to signaling system, so the system we're dealing with here is basically the software of the system. We're looking at, that's the part which is sort of hard to verify in a good way when using traditional methods of verification, with which I mean reviewing and testing. So it's the software. And the software is usually written in some kind of, in a programming language, which could be ladder logic, Boolean equations, a fragment of C or a fragment of Ada, or something similar. But the main thing is that it is very often some kind of Boolean assignment language that we're dealing with. And it's usually in the way, as illustrated by this generic example here, that you have a bunch of Boolean variables. Some of them are inputs, meaning that they provide you with information from the system, surrounding system. And then you have outputs, which is the way for the software to communicate, to send orders to the things, to the physical things surrounding it. And this is executed cyclically, normally, and by first reading of the inputs, and then you update the equations or the assignments in the order given, and then you end the cycle by writing the outputs. And then this goes on as long as you have power. And this is very similar to PLC units used in process industry. And for similar reasons as for the PLCs, you usually want to avoid the computer systems that you use for signaling systems are usually this simple, that you don't want, since it is safety critical and since safety really is a big issue here, you really need to keep things very simple in order to actually be able to verify that it does what it should do. Involving some more general operating system or something would make that much harder. But that's lucky for us, because these restrictions means that what we have here is actually something very close to time positional logic. And this kind of things, this kind of software with this cyclical execution is fairly simple to model actually in time propositional logic. And it can be done, as you can easily imagine, can be done automatically, and that's how we do it as well. That when we have dedicated software to do the modeling for us, it's like just a simple translation basically. So then it comes to the requirements. That's a bit trickier. And there are usually, one could say that there are two main reasons why this is a bit trickier. And one of them is that when one starts look through to determine which requirements that are to be applied and what they actually mean in the given application that you want to apply them on is not always clear. I mean, for instance, if one looks at Trafikverket, the infrastructure manager for the main rails in Sweden, if one looks at their regulations regarding this, it has quite a lot of flavor of a legal document rather. So it's supposed to cover everything in the whole country. Every signaling system in the whole country is supposed to be covered by the regulations they have. But since those systems that we have in Sweden, they are quite they can be quite different in nature, meaning that the actual requirements that you actually want to verify on each of these systems, they will not. You need to massage whatever is written in the regulation, sometimes quite a lot, in order for it to make sense for a particular system. So here one could say that here is really where the domain knowledge comes into play. How this determining thing is actually done, how to do it. You need to know how these systems work in order to do this in a good way. Then there's a sort of logical technical thing is at least in the big as a starting point is a bit tricky, but it actually has a nice solution, and it's that the requirements they are given. If one looks at the regulations, for instance, that those things are given in a general form, like they don't mention a specific system. They speak in general terms, as we will see in an example pretty soon. But when we want to apply them or verify them, it's actually a particular system we want to look at in a particular rail yard. So it's a specific. We need to somehow some kind of mechanism to come from the general form to the specific form that is the ones that we will verify. And then in contrast to the system, the requirements, they are modeled by hand. Meaning that a human has to read these things and try to come up with a proper formulation of them. So here's an example then. So in the regulation, you could find something like this. If a main signal is commanded to proceed and it's the start of a locked route, then the route shall be free of obstacles. Now, since we want, and here hopefully it's clear what I mean with the general nature of the requirement. It speaks of a main signal commanded to proceed, start of a locked route. This is supposed to hold everywhere. So it's definitely not propositional logic that's proper way to model this, but rather predicate logic is much more appropriate. And then we could write a formula in predicate logic like this, which will be very much a model of the statement up here. So proceed for all MSI is supposed to represent main signals, RT is supposed to represent routes, variables. So proceed MSI and start MSI. Yeah, you can see for yourself. It's very much follows. And one should then note here as well that these predicates that occur here in the formula, they are of two kinds. We have proceed, locked, and free, which actually refers to states of the system. I mean, they will be dynamic. A signal will not always be at proceed. Sometimes it will be commanded to proceed and sometimes not. Routes will sometimes be locked, sometimes not. Tracks will sometimes be free and sometimes not. Whereas these start and part off, they are static geometrical stuff. depending on the rail yard. Which signal is the start of which route? Which track is part of which route? So then, as we said then, requirements are modeled in predicate logic, but model checkers require propositional logic. But the really fortunate thing here is that specific systems, they control finite rail yards. So what this means is that as far as the requirements goes, it's an application of predicate logic over finite domains, which is propositional logic. Since by providing finite domain to the variables that are being used, we can eliminate quantifiers by replacing them with conjunction and disjunction, as we can see here. Look at this example again. And now if we put in, referring to looking not all the full example, because that would be too long, too big for one slide. But say we just focus on these three signals. These two routes, the routes that start here at signal 1, one ends at signal 3, and the other ends at signal 5. So what we would do then to eliminate these two quantifiers and this one is then just to use conjunction, since it's all universal quantifiers we have here. So we will have one conjunction for each signal, or rather one conjunction for each combination of signal and route. So we would have, for instance, here proceed SI1, start SI1, RT13, locked, and then we put in all the tracks that I have listed here. So it's TC1 part of if TC1 is part of route 13, then TC1 should be free, and so forth. Now that we have eliminated the quantifiers, then we can start to partially evaluate this formula, since these static things, the start here and the part of predicates, they are statically true or false. So for instance, this thing here, S1 is the start of route 13, so that one will be true. And since it's part of a conjunction, we can just remove it. TC1 will be part of route 13. No, sorry, it will not be, which means that this one will be false, meaning that we can just remove the whole first conjunct here after the arrow, and so forth. So which means that this will just, so the first part here will just reduce itself to this. Proceed SI1, locked R231, track 2 shall be free. Which in reality, it will mean that if this signal shows proceed and this route is locked, then TC2 should be free. Or if this shows proceed, this route is locked, then the same track is supposed to be free. And this also illustrates a sort of crucial and interesting observation that when it comes to the requirements here, or the requirements on the software, what those requirements actually can be in the end is relations between the variables in the system, or meaning that relations between variables in the software. So these things here, the proceed, the locked, the free, which I said represent states of the system, those states will actually be represented as values of variables in the system. So the first thing here, so there will be a variable which corresponds to when signal 1 is commanded to proceed. There will be another variable which tells you whether route 1-3 is locked. And there will also be a variable telling you that track 2 is free. And this piece here tells you that there should be a relation between these three variables. Namely that if the first two are true, then the third one should be true as well. And this is what all these requirements actually boils down to in the end. That's the thing you actually verify. Yeah, so we can have a look at this picture then, which tries to illustrate the flow of things here. That we start off. We start with informal requirements, and for informal I mean requirements written in natural language, which are then modeled into predicate logic or formal requirements. We have specific data, meaning the data of a specific rail yard, where this system is put to control the signaling system for this particular rail yard. That system is translated into a system model. And now we have all the things we need to feed it into our machinery. We have our formal general requirements, we have the specific data, and we have the system model. Then we can start off by eliminating all the quantifiers and partially evaluate, meaning that we will turn these two things into requirements, propositional formulas involving the variables that we encounter here in the model of the system. And then we can feed these things into the model checker, which will then provide us with either an answer yes or a no, and a counterexample showing us how these requirements are actually violated. Yep. So let me just finish with maybe not some, but at least two observations. That one interesting observation, I think, is when it concerns the performance or the performance, if performance is issues when it comes to formal verification. And I mean, as we all know, the general SAP problem is MP complete. So it's the problem of trying to prove a propositional formula, that could, in general, that's very much likely an exponential thing. But in practice, this is rarely an issue. And the reason, I think, this is an hypothesis a bit, but I think that most will agree that safety critical systems, if they actually are well constructed, and most of them are, they are specifically designed to fulfill their requirements in a simple and direct way. That safety critical systems are usually not complicated in their constructions. If something is supposed to be checked when a variable is assigned true, then you usually check it directly, not in a sort of roundabout way by relying on some kind of invariances indirectly. Meaning that safety critical systems are very often designed to be easy to verify. And one should remember that traditionally, just for a few decades back, then there were no formal verification. So these things were supposed to be verified by hand, which means you did tests but maybe even more, you did reviews. And if something is hard to review if it's a complicated construction, then it will be harder to review by hand, even more harder than it will be than reviewing it by formal verification. So I like to think of it saying that this, as far as subproblem goes, the kind of things, the kind of formulas we encounter when we do formal verification in this domain, they tend to be broad but not deep. There are usually a lot of variables, like thousands, but the chains of dependency on them are usually not very long, maybe 3-4 steps at most, which I believe is the explanation why performance is rarely an issue. And then I also think I would like to stress that formal verification do provide much higher coverage than testing and reviewing. I mean, we know that in theory, but this is actually true in practice as well. Because, as we all know, coverage is 100% of the features that you actually have modeled. That's important to remember. That whatever you have chosen to abstract away or forget in your modeling stage, those will not be covered, of course. And this statement is, I can back it up with experience then from all these verification projects that I've been part of. And I say that whenever we do formal verification on a signaling system, we always find errors, even on systems that have gone through regular verification. There's always errors there, which very much support this statement. Okay, so that's the end of my slides. So I'm happy to answer any questions or discussion or whatever. So please.
Thanks a lot, Daniel, for a very interesting presentation. So questions from the audience now. You can unmute and post a question orally.
May I ask a question?
Sure, Jan-Frits, please.
So a long time ago, Prover was more or less founded by Martin Savlund and Gunnar Stålmark. And I'm very curious about what happened to these people.
Well, both of them have left the company for and they've been gone for quite some time, actually. Like, what is it? Almost 10 years.
So they have nothing to do with Prover anymore.
No, they don't.
So at that time there was this Prover technology. The Prover was made by Stålmark.
Yes,
do you still use exactly the same algorithm, or are you now using other algorithms?
No. We don't. No, there's been loads of development since those days. So it's very much a completely new thing nowadays. The model checker that we provide.
Can you say a little bit about the new technology that you use? So what kind of checker technology are you using?
Unfortunately, I have never really been involved in the development there, and I don't really know much about it. So the only thing I know from hearing the guys who actually are doing the development there is that they are very much following all the recent developments in the area. I don't really know much more than that. But it works. It's quite competitive, the model checker that we do with even the academic ones.
Okay. Then from the other perspective, you may have said that in the beginning because I was a little bit too late, but your market, so you're typically working for which parties, especially the Swedish railway company, or are there other companies which form the biggest market?
Let me repeat. So here's
it's clear.
Here's the bragging the bragging page. But our main markets are Sweden and France, actually. That's where we have most of our work. We also do some work in the US and in China.
Okay, thanks.
Thank you. Other questions?
I can throw in one question. Sorry, if someone else wants to go ahead.
Go, please.
Oh, thanks. I need to go off in a few minutes also. But Daniel, thank you for the presentation. You said that you were part of the education, being an assistant professor a while back as well. I have a question on that. How would we prepare our students, let's say at the bachelor's level in computer science, to be able to write propositional logic, timed or whatever? What kind of math courses do you think would be fundamental? We do, of course, typical courses like discrete maths and one variable calculus, multivariable calculus, whatever. Do you think that we need some sort of change in the existing curriculum to enable students do these formal verification things better?
I think it would be very good. I mean, when I did my bachelor things, we had a course, a fundamental course in logic, which covered basically propositional logic and predicate logic up until completeness theorem for first order predicate logic. And I think that's basically covers it. That's what you should know. So,
okay, yeah.
So I think a really good preparation for being able to handle at least formal verification, but also formal methods in general is a general basic knowledge of predicate logic.
Okay, thanks.
May I add something? So in Eindhoven, but there are many universities that offer a standard course in logic. But we also offer a course in automated reasoning where we completely explain SAT technology. That is just part of the curriculum. So it would be good if all computer science curricula would contain that. I have seen quite a lot of students coming in that had no clue, and that is really a bad thing for these students.
Yep.
Thank you.
Other questions?
Yeah, I still have a question. So thanks for the talk. I was actually curious from a technical point of view, what we as a community could contribute to, let's say, your work, or is it entirely based on this satisfiability solving, or are there maybe other issues also that you would like us to address or that we could address?
What would be interesting is, I mean, these things, what I've been talking about here is the kind of traditional signaling systems, or which is usually referred to as interlockings. And with them, they are really built up they are easily modeled, so to speak, in propositional logic. You can handle it with propositional logic fine, right. And everything. So in that sense, we have all we need in order to deal with it. But there is a new generation of signaling systems coming in, being used now, which are called CBTC, where you have, one could say, the signals are not static physical things like car signals and stuff. They are rather, you use radio in order to position the trains, and then you have your routes, but they are kind of dynamic and moving, put it that way, which means that those systems, they involve arithmetic. usually not very complicated arithmetic, but they involve arithmetic. And the kind of arithmetic that they use, it can be modeled with propositional logic, but when you do that, we do encounter performance issues. So that could be something for you guys in academia to sink your teeth into, to come up with solvers, sets, or these kind of solvers that will handle simple arithmetic effectively.
Right. So did you try to use S&T solvers for this, or are they not powerful enough for even what you need?
I think we are using, we use encodings into propositional logic somehow.
Mm-hmm.
But we do, I mean, if one compares to, when we do formal verification on the interlockings, then you can have a running time, even for a fairly large station, you will have runtimes. Runtimes can be counted in minutes, and usually never more than 5. It's usually even faster, like under a minute. But when we're dealing with these CBTC systems, which involves arithmetic, then there can be runtimes of weeks, days and weeks. So it's quite a huge step.
Okay. Yeah.
So that could definitely benefit us if someone would come up with some clever way of efficiently dealing with those kind of things.
Thanks.
Mm-hmm. Other questions? I have a question if nothing else, nobody else has for now. Daniel, thanks a lot for the interesting presentation. So I'm thinking, when I was looking at your specification, I was thinking that this is the kind of specifications that we would, work with in academia. But I assume that yours basically look much more detailed, right? That's, for instance, like an exact location of a train is based on what the balises are giving to you, and then I don't know, the points control are the signals there that you are manipulating are much more detailed. Is this the case, or
no, not really? I mean, it's usually, of course, what I showed here is it's simplified, of course, but in the end, I mean, like, for instance, the way you control a switch, I mean, you have 2 outputs. One run motor left, the other run motor right, and that's what you have.
But this is the logic. I mean, this is the design level verification, sort of, right?
Yes.
You verify the logic, but you cannot verify, or you didn't in what you're presenting, actually, this logic deployed on the ECTS system.
Okay.
Yeah.
Sure. So the reasoning is that this, what you start with is the real requirement, so to speak, is that the switch is not allowed to move in certain situations. Okay, so you sort of backtrack that to, okay, how can it move? It can move if it receives currents in these 2 cables. How does it receive current in those cables? Well, and then you trace it backwards.
Exactly.
And this tracing will give you requirements on how the switch is hooked up to the controlling computer. So in the end, what you will have, so from this kind of analysis, you will end up with two IOs from the actual computer that is controlling the switch. And the requirement not moving will be that neither of these outputs are supposed to be high given certain conditions. And then, which means that you have transformed it, or sort of traced the original system level requirement into a requirement on the actual software.
Yeah, exactly. Thank you.
So in the end, in order to trace it back, so you sort of you make your proof about the software, and then you transfer that result to a statement about the actual switch by then sort of following, okay, so given that now we know the software is okay. So what remains now to check or to verify is that one has hooked up the switch correctly, meaning to those two outputs. It's actually those two outputs which we have verified, which are the ones that control the switch. So that needs to be verified as well, of course.
Thank you. And another question is like, in order to simplify the logical formulas, you need to have the topology somehow modeled,
Yeah.
because you wouldn't know that this track is part of a route or not.
Yes.
So how do you define this topology? Do you define it as part of the assumptions, or how do you do that?
This is, if we look at the flow here, then that information is provided here.
Okay, so yeah, okay.
This is provided here, and if we're going to be a bit technical, it's actually just a matter of defining these static predicates, like start and part of.
Okay.
And you do that by studying the layout of the rail yard. That's where the topology or the geometry is given. So first of all, the rail yard itself will tell you, or put it this way, it will populate the domains of the variables. And so by looking at the rail yard, you will get this list of objects that you actually have. And then looking a bit more, you can also define the static predicates. And that's what ends up here in specific data.
Thank you. And the last question is your model checker in-house? And if yes, is it certified? Is it an in-house one? Did you develop it yourselves?
Yes, it's developed by ourselves, and yes, it is certified.
Okay. Thank you very much.
Thank you.
Other questions?
Yeah, I might have a final question here in the sense of the business model that you have. So not so technical in that sense. So you apply these techniques, it seems, yourselves, but is it also, do other companies also just use your techniques and write these requirements themselves, or is it really, let's say, consultancy in that sense?
It's both, actually. We have examples of both, that typically we would have two kinds of projects, two kinds of gigs, so to speak. One kind of gig would be like that we are given a system and a bunch of requirements, informal ones, and the gig is then to do the verification, which means that we do all the formalizations, we model the system, we do the actual do the formal verification, and what we deliver back to the client is a verification report. So that's one kind of project. And the other kind of project is that we provide the customer with our technology and methodology in order for them to be able to use it on their own. So we provide them with our tools, and we train them in using the tools and the methodology. And then after a while, they are able to use it on their own, model their requirements, model their system, run the tools, doing the verification reports themselves, so to speak.
Okay, thanks.
Thank you. Other questions? Okay, if not, thank you very much, Daniel, for a very interesting presentation. Thank you all for participating. and for the
Thank you.
discussions. And it's finally recorded. I had to reinstall the application, so I don't know what
Okay.
happened, but yeah. And so we will upload what we have. Yeah, except to the first few slides.
Okay. Thanks.
Thank you very much.
Thank you. It's been a pleasure.
Bye.
Bye-bye.
Also
Good.
for us. Bye-bye. Thank you.
Bye-bye.